Have you ever wondered how your car's speedometer knows your speed at a single frozen instant? Calculating speed usually requires tracking distance over time, but at a fraction of a second so small that time hasn't actually passed yet, how can you have a speed at all? Standard algebra is great for things that stay still. It can find the area of a floor or the height of a stationary building. But our world is always in motion. We have accelerating cars, orbiting planets, and fluctuating prices. Algebra struggles here because it wasn't built to handle continuous movement. Calculus was. To measure a moving world, calculus uses two main tools: differentiation and integration. These aren't just difficult math problems. They're tools that allow us to put numbers to motion, helping us predict and build the technology that moves our world. Let's start with differentiation. Imagine you want to find your car's exact speed at precisely the 4-second mark. Differentiation is the process of slicing a continuous action into tiny pieces to find the rate of change at one specific moment. On a graph, this looks like a curved line. Differentiation helps us find the steepness or slope at any single point. We find this by looking at a straight tangent line that balances on the curve at that exact spot, much like a skateboard balancing on a ramp. To find that slope, we use the power rule. You'll see it written with this symbol, d over dx, which is just math shorthand for find the rate of change. The rule is a simple two-step trick. Bring the exponent down to the front, then subtract 1 from the original exponent. For example, to find the derivative of x squared, take that power of 2 and move it to the front. Then subtract 1 from the power. 2 minus 1 is 1, so we are left with 2x. It works for bigger equations too. For 5x cubed, the 3 comes down to multiply the 5, giving us 15x squared. If you have a sum like x squared plus 4x, you just solve each part separately to get 2x plus 4. Differentiation is the ultimate tool for slicing any moving process into its exact instantaneous speed. Integration is the exact opposite. Instead of slicing things down, it takes those tiny, instantaneous moments and adds them all up. It's about accumulation, calculating the total amount of something that has built up over time. On a graph, integration helps us find the total area underneath a curve. We do this by adding up thousands of incredibly thin vertical bars until they fill the entire space beneath the line. Since this is the reverse of differentiation, the math is reversed too. To solve an integral, marked by this long s symbol, you add 1 to the exponent, then divide the whole thing by that new number. If we integrate x squared, we add 1 to the power, turning the 2 into a 3. Then we divide the expression by 3. We end up with x cubed over 3. For 4x, remember that the x has an invisible power of 1. Adding 1 gives us x squared. Then we divide our 4 by that new power of 2. 4 divided by 2 is 2, leaving us with a final result of 2x squared. Integration takes those tiny slices of change and sums them back up into total measurable quantities. These two processes, differentiation and integration, are perfect opposites. It's like a road trip. If you know your total distance, differentiation tells you your speed at any moment. If you only know your speed, integration adds up every second of that speed to tell you exactly how far you've traveled. Because they are linked this way, you can move back and forth between a total amount and a rate of change whenever you need to. This is why calculus is a staple in physics and engineering. It allows us to calculate how velocity changes into acceleration, or how the physical stress on a bridge changes as more cars drive across it. In economics, businesses use these rates of change to find their marginal profit, the exact rate at which their income changes with every single item they sell. This helps them find the perfect price to keep a business running. To recap, differentiation finds the rate of change and the slope. Integration finds the accumulation and the total area. While the symbols may look complicated, these two operations put precise numbers to a world that never stops moving. Now try it yourself. Pause the video and use the power rule to solve these 4 problems. The answers are at the bottom of the screen so you can check your progress.